Welcome to the AbsInt webinar for this release 1704. Now I'm going to present the latest features of the binary-based analyzers, StackAnalyzer, aiT, TimingProfiler, and ValueAnalyzer in this new release version. And let's get started with the graphic user interface changes and enhancements. And the very first point here that I'd like to present to you is the new context-sensitive help, which we have integrated not only in the binary-based analyzers, ACube, but also in Astray and in the rule checker. This feature is available from inside the graphic user interface. So wherever you are at which screen, you can press the F1 key and you will get immediate help by opening the user manual. And I'd like to show you how this is actually working for the ACube for aiT or StackAnalyzer, for instance. So let me show you that in an example. So I've here opened our famous scenario example, which is also shipped as standard example here for the ARM architecture. And I've here 3 tasks: the 1 millisecond, 5 millisecond, and 10 millisecond task. And I'd like to analyze the 1 millisecond task first. And there will be a problem. This was expected. So there's an unresolved computed call inside of routine task 1 millisecond can. And well, now if I do not know what to do with that warning message, I could now use this context sensitive help. I can press the F1 key, and I did that. So immediately the user manual will be opened at the corresponding section, number 9 here, message numbers and handling, and it will show you or give you an overview about this problem, unresolved computed call. It explains how to solve these kind of problems. All right. So this is not only working, this context-sensitive help, for specific warning or error messages here in the message view. You could also, for instance, get help or assistance if you are lost in some configuration view. So let's go to the setup hardware configuration, for instance. So in case of a timing analysis, you typically have to configure the analysis in the very same way as the real hardware is configured. And some points here may be not clear enough, so you can press F1 here as well, and well, the user manual gets opened again in the corresponding view about the hardware view. So the hardware, so let me make that bigger. You see that it explains the various configuration possibilities here, the default instruction set, stack pointer, and so on. So this is available at every view in user interface. All right, so let's come to the next point. It's the AIS File Group view that we have introduced, and this is a central place now where we group all involved AIS files for an analysis. So the AIS files are the annotation files for the binary-based analyzers. And I'm going to show you how this looks like in this example. So let's solve that problem to resolve the computed call here by using a separate value analysis, this initialization analysis, and make this task, this 1 millisecond task, depending on that initialization analysis. So this was a new feature that we introduced in the last release. So let's reanalyze the task now, taking the value analysis into account. And you see the problem has gone. The computed call was resolved automatically. And we now have here a new button, which is called .AIS. If you click on that, you will be pointed to the central place, the AIS file view, and it lists all these involved AIS files to process that analysis here. So first of all, we have the global AIS file, which will be taken into account for all the analysis here specified in the project file, but of course also the local AIS file that is specific to this one analysis. But it lists also, for instance, included AIS files. So in this case, in the global AIS file, I can double click on it and it will be opened here in the editor. We find an AIS file include. And yeah, this central place, this AIS file view will list all included AIS files so that you have one common place to see which AIS files are really involved in this analysis. And the auto-generated AIS files are listed here as well. So the iterative AIS file from the iterative decoding, but also this dependency AIS file that we got since we activated these separate initialization analysis. So I can double click, for instance, on that one, the last one, and I see what the analyzer has auto-generated as AIS annotations to resolve the computed calls. So this was really a nice and convenient way to see which AIS files are involved for one analysis. Okay, let's come to the next feature. That's the new statistics view for yeah, timing or code snippet timing contributions. And I'd like to show you how this is actually working. So let's go back to our scenarios example and let's analyze the 10 millisecond task. It's a Drystone benchmark actually. So this is running through now. And well, we get a result here. And it might be of interest that you got some idea about a timing contribution of a certain path in that task you have analyzed. So let's go to that task routine here, and there's an no, let's go to the proc 0, for instance. There's a loop at the end, big loop, and inside of this loop, several routines are called: proc 5, proc 4, string copy X, and so on. And perhaps it might be interesting to know the timing contribution of that code snippet here, which begins before of the call of proc 5 and ends after or after returning from proc 4 again. So what you could do is you could use our feature that we introduced in the last release. You go to an arbitrary instruction here in this basic block before the call, for instance here, and you say add annotation program point. So immediately a template with a program point annotation will be generated. So we are at 188 bytes after routine entry of proc 0. But let's come back to the graph. We need to specify or to find out what's the program point for the end. So let's go to the basic block after the return and say here the same, add annotation program point. All right. And now I'm replacing the template by this WCAT timing contribution annotation, which is called evaluate. Then I need the first program point, and I'd say up to the end of the code snippet I want to observe, and then I say as and provide a symbol name or symbol that we assign to that timing contribution snippet. So we could say WCAT contribution for proc 5 to proc 4. That's my symbol now, and I have to select if this contribution shall include or exclude the last basic block. So let's take that inclusive. Okay, and if we rerun the analysis now, we will see what happens. I'm going to open the statistics. Well, and you see now here, this is our WCAT overview for routines and loops. So you see the contributions of each routine, and it's containing loops. But there is a new overview which is called WCAT snippet, And this one lists the contributions that we have introduced by the annotation. So our contribution snippet, which we called WCT contribution proc 5 to proc 4, is now listed here. It's contained in that loop proc 0.L1, and it has a total contribution of 16% or 67.66 microseconds, for instance. So this is a new overview that lists all these contributions. And of course, you could introduce here more, and then the list will be filled by these new contributions. All right. So next point in the features of the graphical user interface is the AIS2 has become the standard in the graphical user interface in the editor as well. That means when you set up a new project with the release version 17.04, we will automatically interpret all annotations in AIS2 now. Okay, so you see here AIS2 annotations without this wrapper AIS2 that has been that was necessary in previous versions. So starting with the new version, we interpret in the parser all annotations with for AIS2, and if you nevertheless open older projects, the GUI is smart enough to encounter that we have an older project, an older annotations format, and will apply the legacy, the AIS legacy parsing. You can also influence that behavior if you go to Setup, Decoding. There is an option which is called Use Legacy AIS Annotations. So if you tick that one, then all AIS annotations will be interpreted in the older format. So that means if I run here this analysis, I will immediately get a parser error, since these annotations are, of course, in AIS2 already. Okay, so this is the AIS2 has become standard now in the new version. And the last feature I'm going to present is the fast mode on the support archive creation. So, I mean, if you have some, let me introduce that AIS2 mode again. If you have some problems during analysis and you will contact our support, it's always helpful if you can provide the project file information, including the binary and the AIS files. And the most convenient way to do that is using the help create support archive feature. And this has been extended now, as we also offer a new fast mode for it. So the old mode was that one here. You always needed to recompute the whole information. So that means we needed to decode and parse the binary again in order to determine the involved AIS files and executables. So this is no longer needed for if you want to restrict yourself to the existing information. So that means in our analysis, in our project, we have done already the 1 millisecond task analysis and the 10 millisecond task analysis. And well, this information is already existing now. So we could restrict ourselves to that one. And if I click here, you see it's immediately packed together, and zip archive can be fastly generated. So if I click on recompute information, so all things have to be recomputed. That might take some while in real life projects. All right, so this was about the new features in the graphic user interface. Let me come now to new features in the analyzers and well, also new annotations that are available in this new version. So with this release, we introduced the so-called local call string parameter, and you probably are familiar with the global parameter, so the global mapping parameters, in especially here the max length parameter. You may know that this influences the precision and also, of course, the memory usage for instance, for the value analysis. And I have here given an example. Imagine you have such a call graph where R1 calls R2, but also R3, and there R4 is called, and R6. And imagine further that in R2, a global variable G was assigned with the value 5, and in R3, it was assigned with the value 100. So if you now come later to the R6, probably this G is used to bound a loop or well, address some function pointer array. But if you have a max length of 1 chosen in the global setting, then this means that we will only go back to the latest or the caller routine, and before of that, all this information will be joined. So in this case, at R6, this distinction between this concrete value 5 and 100 may get lost, since so the previous routine was just R4, and here at R4 this information is joined, so that we have in R6 only the information G is lying in an interval of 5 to 100. Of course, you can globally increase this max length now to infinite or to a higher value, but this will influence really all paths and all call chains. There's what would mean that it needs typically much more memory then. Now we introduce a local call string mapping for individual routines. So you could, for instance, say here, as soon as the R6 is involved on my call chain, let me increase my max length to a higher number. So in this example, it would be sufficient to increase it already to 2, but you can also say, let's go to the highest value, which is infinite. Okay, and then the value analysis will be smart enough to distinguish both contexts, either that we came over R2 or over R3, and we will have a very precise analysis then. So this is a new feature, the max length for local routines. Then similar, we offer now a default unrolling also for local routines, for recursive routines. So you can keep the global unroll factor very short. Like in this example, it's chosen to be 1. But if you have a recursive function like this faculty here, you could say, well, let me increase that or unroll that further in order to have a higher analysis precision. And then the unrolling will only be done for this recursive function. Like you know it probably from loops that you could unroll already locally. So this feature is now also available for recursive functions. All right, then let's talk about irreducible loops and recursions. Well, irreducible means you have a multi-entry in this loop or recursion ring, and these irreducible loops and recursions are now also bounded by the defaults that you specify in the graphical user interface. So let's have here an example. So this is an example for an irreducible recursion ring. A calls C, CD, D calls C again, but you can also enter this recursion ring via routine B. And in a stack analysis, for instance, this had to be handled separately. You had to provide an incarnation limit for each edge where you enter this recursion ring, and now these irreducible recursions will also be covered by the defaults. So the default for stack analysis is typically 1. That means if you come over A, you go to C, it calls D, but you will not come back to C again. So this will be the default, and then your recursion is bounded, and the same for entering over B. There's a separate default for timing, since recursions in case of a timing may be different from an incursion limit in case of a stack analysis. So if you do not want to work with the defaults, you can of course also override these defaults by providing annotations now. And I think this was already, that recursion bound annotation for recursive routines, direct recursive routines. This will now also apply for irreducible recursions. And for loops, this is completely new. You can say routine test, irreducible bound 0 to an upper bound, and then all irreducible loops in one routine will be bounded by that value as well. So irreducible loops in recursions are now also handled in a very convenient way. Next feature that is new is the support for C++ namespace. So if you're using C++ programming, you know that we already support resolution of virtual function calls via this very convenient C++ hierarchy or inheritance information. So you can go to the dwarf info and see the inheritance information. You can apply an annotation where you say, well, my computed call should be resolved by class name, : and then the function name, and then the analyzer will automatically find all relevant implementations to resolve that virtual function call along the inheritance tree. And now we support the namespaces of these classes as well. So if you have the very same class name in different namespaces, you can tell the analyzer which class to use in which namespace. And for convenience reasons, you can use this fully qualified name where you don't have to separate the individual namespaces. So that we have a full C++ support now in the binary-based analyzers. And I can already give you a short preview. For the next release, we want to try to also provide an C++ source code analysis. We want to combine that one with the binary-based analysis to even resolve more virtual function pointer calls. And this feature, we hope to have that already available in October 1710. All right, so then next feature is function locals. So static function locals, actually. If you have a local variable, like in this example here, the buffer variable, which is declared to be static, then you will have a global symbol for that variable in the symbols table of the binary. And now you can very conveniently address that variable by putting using the routine name as a prefix, and then with the : variable name. This is then unique and no longer ambiguous for the analyzer, and we can resolve that to find the corresponding address. So static function locals can be addressed now as well. And last but not least, for the AIS2 annotation language, we have some small extension. We introduced by this release the entries functor. And with the entries functor, you can provide an array name, for instance, and entries of this array will, well, extract the number of entries of the given array. And this can be quite useful, for instance, to bound a loop. So imagine you have such an data table array, which has 124 elements here, and you have a loop in process data which iterates over that table. You can now easily say, well, the bound of my iteration loop is just taking the number of entries from this data table, and then this loop will be bounded by 124 actually. So this is also quite convenient, I think. All right, so this concludes my presentation for the binary-based analyzers. Of course, we have many more improvements and enhancements here for aiT, TimingProfiler, StackAnalyzer, and ValueAnalyzer as well, and you can find all of them listed at our website. So thank you very much for your interest. So if you have any further questions, please address us by email or give us a separate call. Thank you very much.
Thank you. Bye-bye.
Bye.